Welcome back to G Fun Facts Online. Today we are dismantling the engine of the modern world to see why it is broken and how we are going to fix it. We often think of the digital revolution as an unstoppable force of nature, a permanent evolution of logic. But what if I told you that the digital revolution was built on a lie, or perhaps not a lie, but a temporary convenience that we mistook for a fundamental law of physics? For the last 70 years, humanity has operated under a single rigid assumption: that the only way to compute anything is to chop reality into discrete bits of ones and zeros, shuttle those bits back and forth between a storage warehouse and a processing factory, and perform logic at blistering speeds. We call this the von Neumann architecture, and while it built the internet, the smartphone, and the space station, it is now hitting a wall. A physical, thermal, and economic wall. Today we are talking about the end of the digital monopoly and the rise of analog matrix computing. To understand why this shift is happening right now, in the mid-2020s, we have to look at the crisis facing artificial intelligence. As AI models balloon into the trillions of parameters, the energy required to simply move data across a silicon chip is becoming unsustainable. We are at a point where we are essentially burning forests to train models that can write poetry. We are building nuclear power plants just to fuel data centers that do nothing but multiply matrices. The digital abstraction is cracking under its own weight. The solution isn't to build faster digital chips, it's to change the physics of how we compute. It is time to teach sand to think again, not by forcing it to count, but by allowing it to flow. Let's start by dissecting the problem: the von Neumann bottleneck. Back in 1945, the polymath John von Neumann described a computer architecture that changed everything. It consisted of a processing unit, which performs the math, and a memory unit, which stores the data. Connecting them is a bus, a highway for information. This separation of church and state, of compute and memory, was brilliant because it allowed computers to be versatile. You could change the software in the memory without rewiring the hardware. But this separation created a flaw that has only become visible recently. To perform a single calculation, your processor has to send a request to memory, wait for the data to travel across the bus, load it into a register, do the math, and then send the answer back to memory. For decades, this was fine because processors were slow. But then Moore's law kicked in. Processors became exponentially faster, while memory access times lagged behind. A gap emerged. The CPU began to spend most of its time just waiting for data to arrive. This is called the memory wall. In the context of modern deep learning, this is catastrophic. A neural network is effectively a massive collection of matrices, grids of numbers. To run an AI model, you have to multiply these matrices against inputs billions of times per second. In a standard digital GPU, like the ones from NVIDIA that power the current AI boom, the chip is constantly fetching weights, the learned parameters of the AI, from its video RAM to its compute cores. Here is the shocking statistic that defines our current energy crisis. It takes roughly 1,000 times more energy to move a byte of data from memory to the processor than it does to actually do the math on that byte. Think about that. 99% of the energy consumed by a cutting-edge AI chip is not spent on thinking, it is spent on commuting. We have built a global computational infrastructure that is the equivalent of a library, where the librarian has to drive to a warehouse 10 miles away every single time you ask for a specific page of a book, read it to you, and then drive the book back before you can ask for the next page. It is inefficient, it is slow, and it is incredibly hot. Analog matrix computing changes the architecture of the library. In this new world, the books read themselves. Now, you might be thinking, didn't we abandon analog computers in the 1950s? We did. We replaced slide rules and vacuum tube machines with digital ones because analog had a fatal flaw: noise. In a digital system, a 1 is a 1. It doesn't matter if the voltage is 4.8 volts or 5.2 volts. The system snaps it to a logical 1. It rejects noise. This allows for perfect reproducibility. You cannot have a bank balance that is approximately correct. But here is the key realization that has sparked the current renaissance. AI is different. Neural networks are inherently probabilistic. They don't deal in absolutes. They deal in likelihoods. They are robust to noise. In fact, computer scientists often intentionally add noise during training to make models better. A neural network doesn't care if a weight is 0.5000 or 0.5001. It cares about the aggregate signal flow. We realized we don't need 64-bit floating point precision to detect a cat in an image or generate a sentence. We need massive parallelism and energy efficiency. We need to embrace the noise. So how does an analog chip actually compute without logic gates? It returns to the fundamental laws of electricity, Ohm's law, and Kirchhoff's current law. The core building block of this technology is the crossbar array. Imagine a microscopic grid of wires, like a window screen. You have horizontal wires called word lines, and vertical wires called bit lines. At every intersection where the wires cross, there is a special device called a memristor. A memristor is exactly what it sounds like, a resistor with memory. You can tune its electrical resistance to a specific value, and it stays there. In an AI context, this resistance represents the weight of the neural network. Now, let's do some math using physics. Let's say we want to perform a multiplication, input times weight. We apply the input as a voltage to the horizontal wire. The weight is stored as the conductance of the memristor at the intersection. According to Ohm's law, the current that flows through that device is exactly the voltage multiplied by the conductance. We just performed a multiplication using zero logic gates, zero clock cycles, and near zero energy. The physics of the material is the computation. But we also need to add up all those results. In a digital computer, you have to add numbers one by one. In an analog crossbar, Kirchhoff's law takes over. The currents from all the memristors along a vertical wire naturally join together. The total current flowing out of the wire is the sum of all individual currents entering it. This means a single flash of voltage across the rows results in the instantaneous calculation of an entire vector matrix multiplication. It happens at the speed of electricity moving through wire. You can activate 1,000 rows simultaneously. A 1,000 by 1,000 crossbar performs 1 million operations in a single time step. And crucially, the computation happens inside the storage. There is no bus, there is no commute. The von Neumann bottleneck is gone. While electronic analog computing fights against resistance and heat, another faction of researchers is looking at something even faster: light. This is optical computing. In processors developed by companies like Lightmatter, information is encoded into beams of laser light. The input is the brightness or phase of the beam. The weight is a tunable mirror, or a Mach-Zehnder interferometer. This device splits a beam of light into two paths. By heating one path slightly, we change the speed of the light, shifting its phase. When the two beams recombine, they interfere. If they are in sync, the output is bright. If they are out of sync, the output is dim. This interference pattern performs the mathematical multiplication. Optical computing is fascinating because photons have zero capacitance. They don't charge up the wires, they travel at the speed of light, offering ultra-low latency. And using different colors of light, you can perform multiple calculations in the same physical space at the same time. This isn't just theory anymore. As we look at the state of the art in 2025 and 2026, this technology has moved from academic curiosity to commercial warfare. In late 2025, researchers at Peking University published a breakthrough in Nature Electronics. They detailed a new analog RRAM chip that demonstrated speeds 1,000 times faster than an NVIDIA H100 GPU, while being 100 times more energy efficient. They solved the precision bottleneck by creating a digital analog hybrid architecture that uses critical control logic to stabilize the noisy analog core. Around the same time, the US-based startup Mythic roared back into the spotlight. Mythic uses standard flash memory cells, the same tech in your USB stick, but runs them in a sub-threshold mode to act as tunable resistors. Because flash is cheap and mature, they can pack millions of neurons onto an affordable chip. Their latest benchmarks show their processors delivering 750 times more tokens per second per watt than digital GPUs when running large language models. Then there is the Titan, IBM Research. Their project, Hermes, utilizes phase change memory, or PCM. This uses heat to switch a glass-like material between conductive and resistive states. IBM has successfully integrated these analog cores with digital communicator networks, creating a tiled architecture that scales up easily. They have even released the AI Hardware Kit, an open-source tool allowing developers to simulate these analog chips in PyTorch right now. However, we have to be realistic. If analog is so superior, why aren't we all using it yet? The transition from lab demo to production silicon is incredibly hard. The first major challenge is the interface. The world is digital. Our cameras, sensors, and internet protocols speak binary. To use an analog chip, we must convert digital signals to analog voltages using digital-to-analog converters, or DACs, and then convert the results back using analog to digital converters, or ADCs. These converters are power-hungry and large. If we aren't careful, the energy saved by the analog computation is lost in the conversion. Modern designs are solving this by using low-precision converters, or keeping the data in the analog domain for as many layers of the neural network as possible. The second challenge is the sneak path problem. In a crossbar array, electricity is lazy. It wants to find the path of least resistance. Sometimes, current flows backward through neighboring cells, corrupting the calculation. To fix this, manufacturers add a selector device to every memristor, acting like a one-way valve or a diode to force electricity to flow only in the correct direction. The third challenge is drift. Analog devices are physical objects. They change with temperature. They age. A weight programmed to 0.5 might drift to 0.48 over a month. The solution here is fascinating. Hardware-aware training. We don't just train the AI in the cloud and copy it to the chip. We train the AI to expect noise. By injecting simulated analog noise during the training process, the neural network learns to be robust. It becomes like a human brain, capable of functioning perfectly, even if individual neurons are a bit fuzzy. The final, and perhaps hardest hurdle, is the software gap. 40 years of computer science compilers are built for digital logic. They expect deterministic behavior. You cannot simply take a Python script and run it on a resistor array. A new stack of software is emerging to bridge this chasm. We are seeing the rise of AI compilers integrated into PyTorch and TensorFlow that automatically handle the digital-to-analog conversion and noise compensation. The goal is for a data scientist to write code as usual, while the compiler does the heavy lifting of mapping that math onto the physics of the chip. So what does the future look like? We are standing at the precipice of the post-digital era. This does not mean digital computers will disappear. Your spreadsheet and your operating system will always need the pristine exactitude of digital logic. The CPU is not dying. It is becoming a manager. The computer of 2030 will be a hybrid organism. It will have a digital cortex, a traditional CPU or GPU that handles high-level logic and control flow. And it will have an analog synapse, a massive coprocessor that handles the intuition, the noisy, probabilistic matrix math of AI and pattern recognition. This hybrid architecture opens the door to applications that are currently impossible. Imagine true edge intelligence, where large language models run locally on your phone or inside a pair of glasses, consuming just milliwatts of power. Privacy returns because your data doesn't have to leave your device. Imagine autonomous swarms of drones that can process visual data in nanoseconds, using optical flow sensors, dodging obstacles faster than a human pilot, all on a battery that lasts for hours. And, most importantly, green AI. Analog computing offers a path to scaling AI to human-level complexity, trillions of parameters, without requiring the energy output of a medium-sized star. The von Neumann bottleneck was a necessary constraint of the 20th century. It allowed us to master logic, but to master intelligence we must break it. Analog matrix computing is more than just a new chip architecture. It is a philosophical realignment of computer science with physics. It accepts that the world is not discrete but continuous. It accepts that intelligence is not about perfect calculation, but about efficient flow. As we look at the memristor crossbars and optical interferometers in the labs of 2026, we are seeing the first sparks of a new kind of machine, one that doesn't just compute, but resonates with the data it processes. The bottleneck is broken, the floodgates are open, the future is analog. Thanks for listening to G Fun Facts Online.